This is the second tutorial in the multi-level linear model series. Specifically, the type of multi-level models that we're looking at the moment is random intercept models. If you haven't watched the previous tutorial in which I covered the variance components model, i.e. where we broke down the variance in a dependent variable across levels of our data, I'd go back and watch that one first because this will be a little bit confusing unless you understand the variance components model as well. So we're going to be working on the same data set as before, and we're going to use the same packages, but we're also going to have Elmer test as well. This just produces p-values for our analysis that we're doing. So if you haven't already installed them, install them, and then we need to get them out of our library as well. And we can also turn off scientific notation as well, so it gives us exact p-values. So as I say, the data set we're looking at is going to be the same data. It's our smoking multi-level data set. Just ensure that you change this to match your location of your version of it, and all these data files and the script can be found in the link below this video. So we'll just quickly run that and then we'll view the data. So you'll be familiar with this data set. It's just like before, which we have our participants ID. So we've got participants, and each participant is measured across a number of days. And within each day, we take multiple measures of their craving for cigarettes. So in the previous tutorial, what we did is we explored how the craving variance falls across the measurement level, the day level, and the ID level, and we found that we had a 3-level structure, in as much as we had measurements that were in days, which was in participants. What we're going to do today is look at the extent that these two variables act as predictors. So we're going to add these as predictors into our regression model, or as fixed effects. The exposed variable is categorical, and it's basically where participants reported being exposed to other people smoking. If it's a 2, that means they're exposed to other smokers. If it's a 1, they were not exposed to other smokers. Cigarettes per week is quite simple. It's just the number of cigarettes that participant usually smokes in an average week. So you can see it's always 51 because that participant always on average smokes 51 cigarettes in an average week. So we just need to fill all that data in. There's some NAs there, and that's just simply participants did a maximum number of 6 measurements per day. So if they didn't do one of the measures, we just have it as blank, and that's not a problem in multi-level models. It will be a problem with standard linear regression. We don't have list-wise deletion in this, so it's absolutely fine. So we're going to build on our multi-level model by adding 2 predictors to it. So first thing we need to do though is we need to tell R that exposure is a categorical variable. So we label a categorical variable. So we just say, in our smoking data set, we want this exposed variable. This is a factor, and it's got 2 levels, and the levels are just 1 and 2. That's what they're labeled in the data set. And we want it to be labeled 1 is none, 2 is exposed. And now if we run that, we can see exposed or none. The other thing that we may have to do, and I'm going to do it, is center continuous predictors. So there's arguments for and against doing this, but I'm just going to do it in this example to show you how to do it. This is going to mean center cigarettes per week. So just write scale cigarettes per week, center equals true, scale equals false. If I write true there, that will turn it into a z-score. As it is, this is just going to mean center it. So it'll produce you a big mean centered output for what everybody's mean centered cigarettes per week is, but we don't really need to worry about looking at that in too much detail. So now we can start building our model. The first thing, I'm just going to do a reminder. This is very useful to have this output of our 3-level variance components model. So we've got craving, and then we've got participant number, the ID, in the data set within days. If you remember what that looked like, here's the output. and this is the amount of variance that each level accounts for. So taken together, that is 100% of variance in our dependent variable, and we can split it up across the levels of our model, and you can see how to write that up in the previous video. I'm not going to recap all that. So if we want to do a model with some predictors in it, we just really can edit our variance components model there. All we need to do is add our predictors to it. So we've added cigarettes per week, and then we've added as factor exposed. And then this is just what we had in previously. So we're just saying it's our 3-level model, and then everything else is exactly the same. And this will give us a model in which we look at these two variables as fixed effects, as predictors, and we see if they are associated with craving. So let's run that. And this is our output. I'll make that a little bit bigger. So we've got our residual variances here, and you can see these have all gone down a bit. And then we've got our predictors. We've got a regression coefficient, a standard error, and a p-value for our predictors. I'm not going to look at the individual predictors now. First of all, we're going to look at these random effects here and what they've done. This is the variance, the residual variance, the variance unexplained in day, the variance unexplained in participant number in their ID, and the variance unexplained at the measurement level as well. And then previously, these were the values here. And you see they've all changed, and that's because our predictors have accounted for some of that variance. So I'm just going to show you on a different screen just so you can see this a bit clearer. So this is the output for our model with the random effects only, and this is the unexplained variance at each level. And then this is the output for the model with random effects and our predictors or fixed effects. And what these values are is the remaining unexplained variance at each level. So our predictors, cigarettes per week, and exposure have accounted for some of that unknown variance, so these have shrank because this is unexplained variance. So you can see for days the variance was 20.02, and now that's gone down to 18.23 because our predictors have accounted for some of that variance, so the unexplained variance has gone down. And then you can see there's a big drop in variance at the participant level, at the ID level, so that's dropped a lot. And also there is a drop in the residual variance, so at the measurement level as well. So our model has explained some of the variance at each of the levels. So that means we can now work out the percentage of variance at each level that the model explained. So to do that, we can just use this calculation. So it's 1 minus 18.23, so the variance here, divided by the variance from the variance components model, times 100, and that will give us the percentage of variance that the model explained. We've got to subtract it from 1 because this value is residual variance. So that's the unexplained variance. It's not how much variance is explained. So if we divide that by that, and then minus it from 1, times it by 100, that is going to give us the percentage of variance the model explained. And we can do the same for participants ID and for the measurement level for the residual layer as well. So this will allow us to work out, so our model with the predictors, these two predictors accounted for X% of variance at the day level, X% at the participant level, and X% at the measurement level. So we can use these two to get an understanding of where our model is explaining variance. So let's go back to the R, and we can enact that. So we can have day variance, so we do our calculation. So we accounted for 8.94% of variance at the day level, 20.64% of variance at the participant level, the ID level, and at the measurement level, we accounted for 3.44% of variance. And we could write that up accordingly, say something like the regression model accounted for 8.94% of variance at the day level, 20.64% of variance at the participant level, and 3.44% of variance at the session level. So a really straightforward thing to write up. So we've basically said these predictors are accounting for some variance, and this is where it's accounting for the variance. It's relatively straightforward, and let's just get our full output again. So we've accounted for this bit, and these are just our predictors. So this is our regression coefficient for cigarettes per week, standard error, and the p-value. You can put t-statistic as well if you want. It's just the critical ratio between the estimate and the standard error. So judging by this, we've got a positive regression coefficient. So there's a positive association between cigarettes per week and craving, and we could just write that up accordingly, like we would a standard regression, really. And then if we look at our factor of exposure, there's a positive association. So it says exposed here, so that means we're comparing when they were not exposed to when they're exposed. So the lower number 1 to the higher number 2. This is positive, so that means after exposure, they had higher craving. And there's our regression coefficient, standard error, and there's p-value, very highly significant p-value there as well. So we can just write those up in a format such as this, so our participants have a good understanding of the two predictors as well. Of course, we are actually missing something that which is probably what we should really add, is we also can get confidence intervals as well. So if we want to get our confidence intervals, we just write confint, and we put in our model. It'll take a second to run these, but there we go. Here's our confidence intervals for our two regression coefficients as well, and of course we can add them to our write-up as well. So it looks something like this. Something else that you may wish to do is the model better than the null model? So it's going to be, we're predicting a decent amount of variance at each level, but what we could do is we could do an analysis of variance and compare the craving model with the predictors in it to the null model which just had the intercepts. So if you run that, there we go, we can see the model is much better. It's a highly significant difference, and you can see there's a notable drop in the AIC as well. So that's another way you can determine the model's better. It's a big drop, and the model is statistically significantly different. So it shows that the model with predictors in is better than the null model as well. So that's essentially how you can add some predictors to the model, understand where they're explaining variance in your outcome. In the next video, we're going to add some more predictors, and we're going to sort of build more hierarchical type models to see if after controlling for certain variables, does adding additional variables predict more variance in the outcome.